Okay, great. Thanks. Welcome to this afternoon's session on fecal sludge treatment technologies. My name is Ruth Cossingham and I live in Durban in South Africa. I've been working with the pollution research group there at the University of KwaZulu-Natal. I met a lot of other people here. I currently work for Faecal, who are an engineering consultancy. The format for today, I think we're going to have each presentation followed by one manufacturer and 2 questions, and then if we have time at the end, we'll open it up to a panel discussion. And can I ask you as well, just during the presentation, if you think of any sort of takeaway points from the session, that would be great. You can think about them, keep it in your head, and we'll come back to them at the end, and that will go into the conference summary. So I'd like to introduce our first speaker. It's Alison Parker from Cranfield University. She's a lecturer in international water and sanitation there. And Cranfield University is a founding member of WhatsApp, and they conduct research together on climate change impacts, groundwater monitoring, sanitation, and lots of other things. She is going to speak about treating container toilet waste in Kumasi in Ghana.
Thank you everyone for coming this afternoon. What I'm going to talk about, as we've said, is a project that we're doing in collaboration with WhatsApp and with Clean Team in Ghana. Now, to start off, I think I need to tell you a little bit about Clean Team. Maybe some of you are familiar already, and it's already been talked about in a few of the sessions. But Clean Team is a container toilet business. So the principle is that every customer has a toilet that's small and portable toilets that can fit in their home. This lady has one actually in her bedroom, but lots of people have them in their bathrooms. So it provides an alternative to the public toilets which most people in Kumasi, in Ghana, where Clean Team are based, use. So the toilet is a container toilet. So what you can see in this photo is the container, the white or the black container that sits inside the toilet, and the container is delivered full of, or partly full of a blue liquid, which acts as a deodorant and a biocide to keep the smell and the sight of the human waste away from the users. It's a urine diverting toilet as well. So 3 or 4 times a week, the service agent will come to the house to remove the containers of the waste and replace it with a clean, fresh container ready for use again. And the containers are taken to a central site where they're emptied. Currently in Kumasi, because there's a big sewage treatment site there which has some waste stabilisation ponds, the container toilets can be emptied into these ponds, and the municipality are very happy with that arrangement. But this isn't sustainable in the long term, probably. It's certainly not sustainable if Clean Team were to move to a different city where they didn't have that arrangement with the city sewage treatment works. So WhatsApp asked Cranfield to look into a way of treating the waste that Clean Team were producing. So we decided we were going to trial 3 options. So the aim of the project was to identify 3 off-the-shelf options. So these aren't kind of research, these aren't currently being researched, these aren't under development, these are things that you can buy off the shelf, and we're trialing them with the Clean Team waste. So the criteria we developed when we were selecting the technologies are listed here. So it had to be able to treat the effluent for discharge into the environment, as specified by the Ghanaian guidelines, which are actually extremely stringent, much stricter than we would have in the UK, for example. So that's quite a challenge. The treatment unit should have a small footprint, so that it can fit on the site that Clean Team already operates in Ghana, but also any future sites. The treatment should have a low capital cost. It should be easy to transport and install, particularly easy to transport if the site is going to have to be moved for whatever reason. the technology should have a track record of extended operation in off-grid situations. The treatment unit should be able to be operated by well-trained, competent staff, but not staff that have a degree, just well-trained staff, but not very highly qualified. And the unit should have a low energy use. So, wow, that's quite a demanding list. And when we started scoping around, we realised that fulfilling this list exactly was going to be impossible. But we had to try and find some technologies that were going to meet this as closely as possible, and that's what we've done. So the first technology we're trying is called SuSanA Biobalsa, and this has uses these 3 tube flow anaerobic digesters, and then they flow into 3 aerobic gravel filters. This system was developed in Mexico for use with animal waste, and they've just started trying it in Mexico with human waste when we approached them, and they've been very keen to work with us on this completely novel waste to see how it worked. So this is a photo of the system installed at Kumasi. You can see the 3 digester bags there, and you can see right at the front of the photo are the holes where the planted gravel filters will be installed. The second technology is BioRock. And this is a system that was developed in Luxembourg for treating waterborne sewage, but we were attracted to it because it does stand alone and it doesn't use any external energy because it uses natural draft to provide the ventilation that the aerobic stage needs. So the first stage is an anaerobic tank which provides initial settling, and then it goes into the second tank, which contains a synthetic media, which is treated with enzymes, which will break down the waste aerobically. And we've imported these from Luxembourg, and this is a photo of them being installed at Kumasi. We've decided to go for 2 of the aerobic tanks, which are the ones on the right, because we're really worried about overloading the system. It's only ever been used on waterborne sewage before, and we're going to try something that's incredibly much more concentrated than that. But the first tank where the solids are settled will require disludging. So the last technology we're going to try is a biofill system. The solids will be emptied into biofill. Those of you that might be familiar with biofill, it was developed as a household sanitation system in Ghana, and it relies on macrofauna to break down solids. So this will try as another novel application to use with clean team waste. So these technologies are in the process of being installed in Ghana on the site where Clean Team are working. And this is our plan for when we get the technologies commissioned, what we will do. So SuSanA Biobalsa will start with 1,000 litres of the waste a day, scale up to 100 litres, scaling up to 1,000 litres. The BioRock system will start with just 50 litres a day and scale up until we get either a 2-day retention time, or we're really worried that the system's going to fail because it's not kind of optimised for the kind of waste that we're treating. And the biofill system will receive the sludge out of the BioRock system. We'll collect samples daily and test for pH, alkalinity, ammonia, COD, temperature, turbidity, and the presence of the dye in the final effluent. So the blue dye that you saw in the weight in the blue liquid at the beginning, we'll see if that persists through the system. We'll also do weekly tests for total solids, volatile solids, and E. coli, and daily tests, and keep a diary on how easy the plants are to operate. And we'll also do phytotoxicity trials every 6 weeks to check if the chemical biocide still persists. So I'm afraid I don't have any more results to present to you today. This is still trial is still at quite early stage. It's taken us a long time to get to this stage of having the technologies installed. Having said that, this gives me a great opportunity with so many brilliant minds in the room to get any feedback which we can actually use at this stage to improve the project going forward. So please do give me any feedback, any questions. These are my contact details, and also if you're interested in finding out more about Clean Team, I know Andy now is presenting at a workshop on Thursday, and you can also check out Clean Team's website just there.
Great, super, thanks very much. Are there any questions specifically for Alison?
Thank you very much. My name is Philemon from Botswana. Thank you very much for those technologies that are very interesting. But for your second technology, I don't know whether it's the bio-rock. Yeah.
Yeah.
I can see that it is, you know, in deep underground. I can see that it's deep underground, and I'm wondering, in cases of high groundwater table, won't we have, you know, problems of, flotation?
Yes, basically, I think that could be a problem. The site we have at Donkwasi, we don't have a problem with groundwater there, so it will work well there. So, yeah, I think that's definitely a problem we have to consider when Clean Team move to different cities, if they're selecting new cities, new locations for doing this waste treatment, if this is the one that we go for, and in fact the Sistema Biobolsa is buried to a certain extent as well, so we would have to sort of suggest that they found a site that didn't have a high groundwater, or we have to work on other solutions to stop the flotation.
Any other questions?
Hi, Jess MacArthur here from ID. I'm just curious, we're doing a similar project, or not kind of similar, in urban Dhaka in Bangladesh, and we've had a really hard time getting the systems into Dhaka. So I'm just wondering if there was any learnings from the actual procurement of these technologies and getting them to the locations, and if you can just give any examples of how that was difficult or easy.
So yeah, it's difficult for sure. So we were lucky because Clean Team is supported both by WUSUP and Unilever, and Unilever already have quite a lot of experience in importing things into Ghana. So we used the route that they used, but I guess the first tip is try and find people who've done it before, specifically into Bangladesh, and use the way, take their learnings. Our second tip, which seemed to work, was air freighting stuff rather than land freighting stuff, because apparently Aqua Airport is quite a small holding bay, so the customs people are keen to get it shifted out, whereas the dock apparently is a huge holding bay, so things get stuck in the dock for ages, but obviously the air freight costs are quite a lot more than the land freight costs, so depending on the size and weight of what you're importing, it could be a...
And local manufacturer, how does that fit in?
So the Sistema Biobolsa system is quite low tech, so I think ultimately we could move into local manufacture for that. The BioRock system, there are septic tank manufacturers in Ghana, so we did consider using Ghanaian septic tanks and kind of using the same media for BioRock, but we thought for the first trial as a kind of control version, try not to change too much. So moving forwards, we could use a local manufacturer for that. And then the biofill system is manufactured locally.
Okay, I think we're going to stop it there, and any other questions, hopefully we can take at the end. Thank you very much. It's great. I'd like to introduce our next speaker, who I hope is just through the seat, because I can't actually see him right now. He is Osbert Abidukwe, and he has a civil engineering degree from Makerere University, and he's currently doing his master's there as well in civil engineering. He also works for Water for People as a sanitation engineer and the SANI coordinator, and he heads the technical team for Faecal Sludge treatment. And the title of his presentation is Testing a Low-Cost Decentralized Faecal Sludge Treatment System.
Good evening. My name is Oswald Abuche, as she has said. I'm going to discuss about the Singapore Faecal treatment system, and commonly call it the first technology. We are doing it in partnership with the Water Research Commission. And Water for is an NGO that is based in the USA, and its vision is to provide to make sure everybody has access to safe water and sanitation. And the Sun Hub, or the Sanitation Hub, is the key program that ensures that we give sustainable sanitation through action research. We develop our technologies in partnership with both local and international partners, and the key ones in Uganda we normally use cases, we work with KCCA, National Water, and Makerere Cluster, and we have some students and working with on this project. Those of you who don't know where Uganda is located, it's in the East African region. It's in the East African region, and our main office in Kampala here where we do most of our projects, and this project I'm talking about is located in another project now. Faecal sludge, I don't take it for granted. It's sludge of variable consistency which has been captured in our sanitation systems, like latrines, septic tanks, and power flush systems. And faecal sludge can be raw, partially digested, semi-solid. For example, this one here, in this case, which you normally have to see on our pilot plants, you can turn it as maybe semi-solid sludge. You know, the presentations I've seen, I've seen people making sludge of such thickness. Overview of faecal sludge management in Uganda. In most towns in Uganda, we use wastewater separation ponds. We have about 3 conventional treatment plants, and only 1 plant, and the recent one has been designed to handle faecal sludge. And some towns which have no treatment plants at all, and have taken some of our technologies, as you saw yesterday, the garbers. When they garb, at times they just dig and burrow inside the sludge. That's how the situation is, and they have nothing in there. Then the faecal sludge in Kampala only has about 7% seaward, and this is the biggest percentage in the whole country. If you take it at the national level, it will be like 2%. And the key structures we use are normally VIPs, and septic tanks, and some power flush systems. And the key challenge we face, our city has a lot of traffic jam. You go the whole day, maybe you're going to empty a latrine which has a lot of solid waste. 2 hours you're fishing, 2 hours you're garbing. The other 2 hours you're moving from maybe 10 kilometers to dumping site. You only use about 6 hours. 1 hour you're dumping, for the 7 hours and you have 8 hours to work, and you find you can't go around, you can't go back and some. So I've talked about garbing, this is the whole summer about garbing. You empty some of these places are not accessible, so you move about 100 meters to pick up, you load, then you come and do summarizes our garbing business and how the treatment is fit in the garbing business. Now, about the first pilot project, as you can see the units under it, you have the inlet with the screening tank. We saw yesterday that in start we normally have a lot of solid waste. So this tank was basically to remove the solid waste. Then we have the sedimentation unit, which we commonly call the watering unit, where the sludge is watered and some central solids are moved. Then we have a big bubble reactor. This one we're looking at move of organic pollutants basically. Then aerobic filters, we're looking at move of suspended solids. Then also we move some pathogens which can be trapped by that biofilm which is expected to run the media. Then we have aerobic planted rubber filter here, we're looking at move of smell and maybe taste color. Then we have an unplanted drying bed which is roofed, so that even if it's a wet season, the drying is almost constant. And this is basically to do secondary and tertiary watering of the digested sludge from one digested. And that's the schematic. If you look at it, it looks like what Florida is already doing is decentralized water treatment systems. But here our only difference is that we are trying using plastic tanks. Some people in Uganda who may want to do garbing business may not handle those concrete materials to establish a centralized treatment system. So we try to maybe use plastic tanks and simulate what Florida exactly does and see how it performs, and we shall see the results of what we are getting. That's detailed drawings. I will not go into it since we've already seen the schematic. The details you can you access my presentation here. And the key facts about our plant, it's on a small plant, 6 by 6 plot. We are loading it with about 500 liters of sludge per day. We are looking at the hydraulic fermentation time of about 10 days under normal conditions. I'm not considering the planted rubber filter. And we are looking at about 3 to 5 weeks for watering the unit. I know when conventional digesters should be like months or so, but here, because it's also working as a watering unit. And we are receiving very thick sludge, so that's why it's more does of watering than the anaerobic digestion. Then we are so far treated about 44 to 50 liters of sludge, and upflow velocity is about 0.5. That was the count for constructing, and that was sampled to guide us in the design. Some of the pictorials, the plan, that's how the pipes are inside the tank, and this is showing all the how they are arranged, and this is our drying bed. Results from the monitoring. The load treatment should improve its efficiency, should improve its time. So we are supposed to monitor maybe like every after month. This was our first time, our first month of monitoring. We are looking at effluent concentrations. We are basically looking at COD and BOD. Since we are doing action research, we want to take it to scale. But we have students who are going to other parameters, nutrients, pathogens, and so on. But our key ones were basically BOD and COD. Then you see the effluent, we're getting about 20 for COD and maybe 12,000 in the initial sampling for BOD, and we reduced them by over 90%. But since it's a very concentrated sludge, the quality was still very poor, the effluents, about 800, about 1,000. Yet our discharge standards say about 100 for COD, 100 for total suspended solids, and 50 for BOD. So it was still up. Other samples, that's maybe sample 3. This one we're moving, the trend was a bit funny. We're getting suspended solids reducing, but the BOD and COD were remaining a bit constant, a bit 1,000. So meaning the reduction was not so significant. And when we checked, it was checked with our loading, what we loaded in that period, it was more septic sludge, which came from a septic tank, and it's normally already digested. So the reduction is not so significant, so it kept almost on the same curve. Then we are looking at sample 5, results here were almost meeting the discharge standards. We're able to reduce COD to about 143, our discharge is 100, recommended. Then BOD was about 100, yet it's 50 required. And the efficiency was also about 99 and so plus. Those of you who don't enjoy bar graphs, we have put a sample where I tend to summarize and see the trend is the same here. We are looking at efficiencies of over 93%, but this was sample 4. One before the sample 5. The discharge standards here were 400 for BOD, 800 COD, and 340 for total suspended solids. Now it's very hard to compare what with the improvement with time. Because today we receive sludge maybe from septic tank, tomorrow from a public latrine, and tomorrow from an ordinary latrine. We have no equalization tank, so we can't get a uniform effluent quality. So we are now looking at each sampling to just see what we've been able to move. Overall efficiency, as I've said, you can see it's almost generally above 70%, about 99 so plus. And these are just a summary of whatever I've been saying. We normally sample, even every unit is equipped with some sampling tab, where we normally tap sample on a monthly basis. Physical challenges, everybody yesterday was shouting, who was doing empty was shouting about salt waste. It's a problem while empty, and so it's a problem while empty. You get a lot of salt waste. Personally, I've never seen using pads. It was my first time to see them when I was doing with this sludge. Then we also have variation in properties of sludge. They can vary from 1,000 to about 50,000. Now, it's very hard to design for such a sludge. The organic loading rate, you can just have to give a range. Then, accumulation of scum in the biodigester one is affecting our biogas production. Then, slow watering ability. If we get a better watering system, we could be able to treat more than 400 or 500 liters of sludge per day if we can be able to water our sludge in a very short time. about reducing progress, what we've been able to do, we are looking at using the biosolids themselves to do some aquaculture. We are looking at, we've started producing some briquettes. We are looking at biogas, and we are looking at vermicomposting with tiger worms. Here we just roasted it with some dry sludge, but I put question marks, don't eat, because of what I'm about to say. What conclusions? We can see our efficiency is about more than 70%, about 99%, but most of them actually are in 90s. Though because of its strength, this charge stand is still a little. Then we have, I was recommending that we should, in future when we are scaling up, I'm thinking of putting an equalization tank so that it can ensure aerobic system uniformly. Whether it's from a septic tank, a petri latrine mixed together, I can have an equal loading in terms of organic loading rate onto my system. Then, now off topic a little. In computer language, they say garbage in, garbage out. Cows or other animals take pathogenic feeds, they produce waste. We are all very happy to use it without fear. Man takes very delicious food with no pathogens, but when he gets out what he gets out, we are all very sad about it, even when it smells or it doesn't smell. And as a result, we contaminate it more. Everybody think in my country, for example, a broken bottle taken in a latrine, a rag taken in a latrine, used meaning tablets taken in a latrine. As a result, it becomes so contaminated. Yet, when you look at it, if, for example, if this sludge had been dried and I just used it to roast my maize, I wouldn't have feared eating because I know the pathogens would have been kept in that what? In the fire. But because of what we put, poisons, you may eat that ash on the maize and get sick. So if we could all become happy on using our food, on handling our food sludge as this man is happy handling cow dung, which even smells more than the feces, I think we would have less problems via treatment of our food sludge. That's the point. Thank you very much. Thank you, WRC.
Thank you very much for that. It's definitely difficult trying to treat such a variable feedstock, I think, into the plant. We've got time, I think, for a question at the back there.
Okay.
Yes, hello. Thanks, Osbert, for this very informative and actually excellent presentation. I'm always appreciating the work Waterfall people is doing in Uganda. Lars from Sanitation. I was wondering about, given the very high load of COD and the influence of the areas of the liquid effluent, like did you at all look into like sludge accumulation rates inside the areas themselves when you were looking at, you know, like the digestion rates and when you're doing the sampling, have you heard anything about the sludge accumulation rates inside the areas?
The sludge accumulation rate in the ABRs, we have two tanks, as I've said. This one here. We have this first tank and this one here. Because of our very thick sludge, some salts normally escape to this tank. Our design says when it gets to about a third of the tank height, we should disludge. But this one normally happens like in 3 months. For example, this plant has been operating for 7 months now, and we disludged in October. It was getting almost half. But this other one, we haven't disludged still less than a third of the height of the tank. So, but I haven't calculated, like say, that measure rate per month is like this so far.
Great, thanks.
One more quick question.
What is the pollution levels in the outflow from the septic tank? This is about the sludge. Probably you would have measured the pollution load in the outflow coming out of the septic tank because Uganda is yet to be covered with a comprehensive sewer system.
Looking at only sludges from septic tanks, when we are designing for septic tanks, they give about 3 years sludging interval, and if the sludge has been kept for all that period of time, you expect it to have undergone almost complete digestion. So maybe it could be in a thousands. I haven't characterized it specifically for septic tanks, but literature maybe be less than even 1,000. Waste has been already digested inside the septic tanks. But for latrines and public latrines especially, there you get very young sludge, which is normally so concentrated down the pollutants.
Thank you very much. Move on to our next speaker, who is speaking on pit composting and a solution to enhance the treatment of fecal material from urine diverting composting toilets. Could I ask the speaker to come forward and introduce themselves? Because unfortunately I don't have a bio. Sorry. Oh, it is supposed to be. Okay. The Director of the Institute of Environmental Science and Engineering at Hanoi University Civil Engineering.
Thank you, Chairman. Good afternoon. In fact, my PhD student should present this paper, but we have some work, so I decided to invite the works today. This is my turn, so I'm happy to present this paper on behalf of the whole team. You know that we are facing a problem of fast filling up the pit of the on-site sanitation systems, and here, so what we are trying to do is to enhance the decomposition process of the pit and after the pit, so that we could have safe fertilizer use in agriculture. So this is the ongoing work, and we would like to present to you the initial results. In Vietnam, most of pit latrines are added after every time of use, the ash, and sometimes they add the lime. They think that it is hygienic. But because of adding high pH ash and lime, we have very high pH environment, and it kills also useful bacteria into the pit, in the pit. And from the previous presentation in the morning section today from our team, you will see there is almost no biological decomposition within the pit. So we have to enhance it either within the pit or after it. So one way to do it is try to find a cheap aerobic composting process to further decompose the fecal material. And here, what we are trying to do is to introduce aerobic composting with manual steering, so that we could have a better aerobic condition. And we try to find local bioadditives which are available in the market and which are cheap, which have the good decomposition of hydrocarbon, carbohydrate, which have also ratifiers and good enzymes for decomposition. Here we are testing the composting after the pit using the drum system. This is a cheap plastic drum with one axis, and manually from time to time you can rotate it. We add the fecal material together with sawdust to control moisture. We add it organic waste. Here we add food waste to control the C/M ratio. And from time to time, the drum is rotated. We have different drums with different mixing ratios and different types of bioadditives. These are parameters we are analyzing. We measure also temperature over the time. This is automatic temperature record put inside the pipe, inside the drum. the first drum, we add Faecal material with the bioadditive called shaggy bio. It is a combination of carbohydrates and nitrified material and food waste. The second drum we add with alcohol yeast, which is a very local material in the market, and farmers use that to prepare alcohol. It should have a good carbohydrate decomposition. Food waste and sawdust for control moisture and C2M ratio. And the control drum is just Faecal material and sawdust and food waste without bioadditive. So the results we see here, the temperature of the first and second drum significantly increased, especially for the first drum. We reached 44 degrees, which was very good, while ambient temperature was around 20. For the drum 3, we didn't have it, just ambient temperature. This graph shows VS reduction. We don't have much VS reduction as expected. And, nitrogen reduction is significantly happening in the drum 1 because of high temperature with rapid mineralization of organic compounds. Very good results in the E. coli reduction. In the drum 1, we have after 4 months, 4 logs reduction. The same in the drum 2, 4 logs. In the blind drum, we have 1 log reduction. Conclusion. With local available bioadditive, we can enhance the decomposition process after the pit. And we may also apply bioadditive also within the pit. We can reach the temperature. Can we come to the papers now? Papers. Okay, next. Next. Forward, yes. With the shaggy bio, this is a locally produced bioadditive made for solid waste treatment. We could increase the temperature in ground rapidly, reach 44 degrees within a few days, first few days. And that led to the idea to enhance the mixing process with an easier operating system. And these results lead us to create a new prototype of a new composting toilet, which you see in the booth here in the corridor, where we have a screw, and manually you can rotate the Faecal material. We can mix it, and there is a pipe where you can add the sawdust and bioadditives if you can. So this is the idea to enhance the decomposition process, and we see it works. So it's one of the potential way to improve the pit hatchery. Thank you very much.
Thank you very much for your presentation. Any questions?
Okay.
Thank you so much. I am Wasif Kashmir Baba from Pakistan, and I have a single question with you, please. You have talked again and again about temperatures to control the feces and management. Would you please discuss how do people control the pH level for all this process? And second one, you use sawdust. And is it possible to use any other thing like ash, like tissue papers to accumulate and moisture control as well? And the CM ratio, as you have discussed, I think so. This is a little bit below than is internationally and scientifically required. And the fourth one is why assume people use the vermicomposting or humidifications in your products as well? If not, how do people deal the ground water contaminations about this leaching material as well? Thank you so much.
Thank you for the question. Shall I answer directly to the questions? Talking about adding material, we have a different way, and any local material you can find which can provide, because in this toilet, if the moisture is there, you cannot have good aeration, you cannot have aerobic decomposition. So moisture is important, and we know that good moisture value is aerobic composting, 60%, 55, 65. So the role of sawdust is there. Besides, we have some C2N control. You can add rice straw, but not ash. Ash may increase pH significantly, and all the good pathogens can die off. So the way you can do with ash is you add in the beginning, and after that you don't add every day. You take the material out and start to do composting with other materials. We did very careful analysis, microbial analysis with colleagues from London School of Hygiene. Much less microbial community in the pit latrine material where people add ash and lime. Much less by microbial community diversity. How to control?
There was a question on the composting aspect and possible pollution of the groundwater. Is that correct?
Yeah, groundwater contamination. This is a good way to protect groundwater if you have a dry toilet, if you have compost. And they have been above ground, they are not using water, and they are not discharging wastewater to the ground. Of course, you have to be in the right place where it's not flooded and far from the water well. So this is a way to protect groundwater. Of course, the system is a bit. I would like to address the first question, if I correctly. This is not simple system. So we have in the booth. You see, we have a screw, and we try to reduce the cost of the device and make it simpler as much as possible, usable for people. What is the last question?
Was there one further question from that?
C2N ratio, I think. Yeah, we know the best C2N ratio for composting is 25-30 C2N, and we try to achieve it. And by adding other types of waste, if you can, and we can give we can try different types of waste and give advice to the farmers, to the people.
One more question. Nothing at this stage. Thank you very much for your presentation.
Thank you very much.
To introduce our next speaker, who is from Bangladesh, Mr. Digbijoy Day, and he will be speaking on filled up twin pits to organic fertilizer, action research results from rural Bangladesh. Today is a senior sector specialist working in the VR Exceed Wash program. He has a degree in biochemistry and a postgraduate degree in molecular biology, and his research area is sludge treatment, anaerobic and aerobic digestion.
for giving me the floor. Here I am representing Water, Sanitation and Hygiene program, and the topic will be reuse of fecal sludge as organic fertilizer in context of Bangladesh Wash initiative. Basically, I have to confess that we are going to talk about the rural situation of Bangladesh. And before starting my presentation, I would like to thank Bill and Melinda Gates Foundation for supporting me. Okay, let's start. In our program, we have provided more than 1 billion double pit landfills grant to the poor people. So here you can see the model we are following. People use the first pit, then when it's filled up, then they go to the second one. So they need to be emptied to keep them usable. And the question comes to our mind that what to do with the fecal sludge after emptying. So from this point of view, we have designed the research, and in next few slides, I will tell you about the research. I mean, what are the things we have done. The research aims to actually meet the nutrient content at National Organic Fertilizer Standard and contribute to the agricultural system of Bangladesh through fecal sludge-based organic fertilizer. I have to tell a little about the National Organic Fertilizer Standard because Bangladesh Agriculture Ministry has its own standard for organic fertilizer, which is more or less similar to the international standard. And we are focusing on the second point very carefully. That's because in that case I have to talk about our agricultural system a bit. Bangladeshi farmers mostly depend on the chemical fertilizer for their cultivation, and you know that this is not very good for the soil in the long run. So at the time we are planning to compensate the soil for the nutrient through the fecal sludge-based organic fertilizer. In the pictures you can see that how we are actually planning to do our work. So here you can see that how the anaerobic digestion occurs. Basically, as when the first pit filled up, people start using the second pit. So naturally the sludge remains inside the pit for around more or less 18 months. So anaerobic digestion is the process continues during that period. We have started our sample analysis by collecting samples from 7 climatic zones. You can see on our right in the picture. We have collected 10 samples per zone. So after collecting the samples, we have done physical and chemical parameters of these 7 samples. At the time, we have done microbial and pathogenic analysis as well. So we can see that there are some deficiencies in nutrients. One is that the moisture level is too high, and they are a bit low in pH, and also a bit low in potassium. So what we have done is that we have gone for co-composting with sawdust and sun drying. Why we have gone for sun drying, I will tell you in the next slide. But we have done co-composting with sawdust. Basically, we can do that with other agricultural residues as well. But as in the countryside, I mean in the villages, sawdust is available, we have preferred to use the sawdust. Here in the graph, you can see that how this procedure helps us to raise the pH, make the moisture lower, and increase the potassium content. Okay, here comes the pathogen part. Though we have sampled after 18 months of storage, still there were anaerobic digestion, but still we have found some pathogen in the sludge. So that's why we have applied sun drying, and you can see that after sun drying, after 7 days of drying, we have found no E. coli in the sample. After 15 days of drying, we have found that there is no Clostridium perfringens. But it's the helminths, or more precisely the helminthics, they are so persistent that it took around 60 days to make all the helminth eggs are non-viable because actually they do present, I mean, they remain in the sludge but in a non-viable form. So here in this slide you can see that actually what in the graph you can see that how we have moved and on which phase we are right now. We have done the nutrient development part, we have done the pathogen removal part, and we have completed the field trial as well. You can see two pictures. We have done field trial on rice and on cabbage actually. So this part has been completed, and right now we are working on marketing and supply chain development. Basically, before going to the next slide, I have to say one thing that we have found one advantage in working in the rural area than the urban part. That's because the ultimate target of reuse of fecal sludge is the farmers. I mean, they are our target customer. So the advantage is they are actually in the rural part. So the customers are in the surroundings. So one entrepreneur can easily collect the sludge from his surroundings. He can go compost it and he can sell it to his nearby farmers. So obviously the transportation cost minimizes a lot. So there is no question of external funding or subsidy. The whole business can remain viable by itself. Before completion, I would like to inform you about some other works we are currently doing on fecal sludge management. Here you can see we are also trying to do co-composting of fecal sludge with kitchen and market waste. In the diagram you can see the idea of it. We are also trying to do biogas generation from the mix of fecal sludge, corn stover, and chicken manure. And at the time, we are trying to introduce mechanical peat emptying through Faecal. Actually, we do work in the rural area, but these three action resources are for the villagers, those who are in the surroundings of small towns or towns. So we are, along with our ongoing work, we are trying to introduce these things as well. So this is actually from my part. Thank you very much for listening.
Thanks for the interesting presentation, and actually thanks to all our speakers for keeping to time so nicely. Can I take any questions? Front row.
Moritz Wolf from SuSanA. Thanks for the excellent presentations. I'm here. I have a question. Helminth eggs. You said there were different climate zones. How was the distribution of helminth eggs in the sludge which was digested after these 18 months? Were there some where they were totally inactivated? What was there a certain percentage, some pattern you saw? Because, yeah, some people are saying, I mean, in other countries also, other people say, oh, there's totally die off and they just use it. It seems there's no understanding of.
Well, I have to say that it's really not very easy to kill all the helminths in just one process, because if you review the papers, you will find that there are different papers and every single paper is talking about every new technology and temperature to kill the helminths. But in our research, we have found that, as I have already mentioned, that there are 7 climatic zones. Especially those who are in the southern part, the moisture is a bit high in the soil, and in those areas we have found that the helminths are actually still viable. I mean, after 18 months. And for that reason, we had to apply the 60 days of drying. Otherwise, in the northern part, we have found that most cases there are no helminths, and in some cases we have found helminths, but the eggs are not actually viable.
Yeah, in fact, a very good presentation about a closed loop system. So environmentally it makes a lot of sense.
but have you done any analysis of the perceptions of the adopters of two-pit toilet about acceptability of this toilet vis-a-vis other toilet, as well as acceptability of the farmers of this fertilizer, and whether any perception of the stakeholder consideration? Well, I would love to answer that question. Well, when we have started our program, definitely we have started our program with single pit lattice. But when we have talked with the people, we have tried to analyze the perception of the people, those who are in the countryside. And after having their perception, we have started to provide double pit lattice. So definitely we are doing this with their consent. And can I have the, can you repeat the second question again? It is about the perception of the farmers, about acceptability of this as a organic manure. Well, when we have started our Faecal management part, I mean the research, in that period we have done a complete survey on the willingness of the farmers to use that. You will find it rather interesting that when we have asked the farmers whether you're going to use that as a organic fertilizer in your field, everybody, almost everybody answered that no, we will not going to use that. But when we have told them that after the digestion period, the sludge fertilizer will be completely odorless, it will be grinded, so will be in a very easily usable and good looking form. Then they replied that yes, we can use that, and we have done that actually. We have prepared the sludge as organic fertilizer, and when we have delivered that to the farmers, then they have said that yes, we can use that. And you have seen two pictures of field trial where we have done that with local farmers, no research farms. So then they have replied that yes, we can do that, and we can do that easily. That's it.
We can take one more question.
Hello, Jess MacArthur from Bangladesh as well. Just a follow-up question as well on the last one. I'm thinking a little bit about the marketing and supply chain development. And just what I see into these rural areas is some farmers are okay to dump it on their own land. And so how are we going to convince them to use this more sophisticated system? Because I think the farmers who would quickly uptake this technology or quickly use it are the farmers that possibly would be using waste that they would take out of their own pit, they self-empty, and then lay it on their crops. So what's the marketing going to look like?
We are not expecting that it will be done just like that. Well, definitely it will take time, but what we are focusing on is that we are trying to develop kind of plot demonstration in different areas of Bangladesh, and previously we have seen that except talking and advocating the farmers, plot demonstration is a very good way to convince them. I believe we have already done that in some areas, and definitely we are going to implement it in the other parts also.
I think we'll have to leave it there, but I think we will have time for a panel discussion afterwards, so we'll take more questions then.
So thank you.
Thank you. Our next speaker is Dave Wilson, who comes from Durban in South Africa. He is an engineer with eThekwini municipality there, which is in Durban, and he has 35 years experience in wastewater. He's currently the manager of the wastewater networks of the municipality. And he will be speaking on tips of the tree emptying program and processing that sludge through the LADEC process.
Good afternoon. I don't want to say good afternoon or good evening, but I think we're halfway between, but it's fantastic to see a tremendous turnout at this time of the afternoon. Yeah, my name is Dave Wilson. I'm from eThekwini, which is in South Africa. It's the city of Durban. The metro area is called eThekwini, and I'm responsible basically for the sewage networks within the eThekwini area and pump stations, etc. What I want to talk about today is a pit dream program that we embarked on in eThekwini. Our city council passed a resolution that they would empty every pit once in every 5 years at free. And thereafter, if they were abused and filled up rapidly, then the owner would pay a full cost to empty their pits. And we're only talking about VIP pits here. We're not talking about UD toilets or anything. We're purely talking about the VIP pits. 2007, we embarked, we decided to claim 35,000 pits, which is how many VIPs we have in the area, and to use labour, because we found it was the most cost-effective method of working, especially with our pits. Our pits are dry pits, generally. They're not wet, so labour was the best method. And we were going to dispose of the sludge in the most environmentally acceptable method. The contract was advertised. It's a 3-year contract. We're limited to 3 years in our country. And through our procurement section, we employed 6 subcontractors. We in turn employed 6 teams made up of 6 people. That was the staff complement to do the pit emptying. Key issues with the contract that we had was health and safety. Every person that worked on it was given a medical, was given an entry medical and an exit medical. They were provided with work tablets. Tools and equipment. We had all various types of tools and equipment that we used, we developed on site. Removal of sludge from the site was not easy, but we got it, and disposal of sludge. Those were the key issues that we had to deal with. Very early on in the contract, we found that there was problems, space and access. A lot of these places where they had VRPs had been infilled, and it was very difficult to get in and around them. Pathogens. In Tekwini, we have a major problem with the story. We found that the pathogens we thought would die off after 18 months. Some tests were done with UKZN University and Colin Archer and Co. And we found that after 15 years, 14 years, there was still evidence of live Australia eggs. Water, excess water, sludge has got excess water in it. Detritus, we have a big problem with detritus in our areas. We've got full of rags and bottles and all sorts of stuff that comes in the actual pittery. And then sludge disposal. That was the problem. That became the big problem. So what we thought about sludge disposal, we thought that we would bury on site, and we found there was space constraints. You couldn't actually bury on site, and also we found that due to the pathogen problem, we didn't want to bury sludge on site that was full of pathogens and going to be there for the next 14 years. Disposal of landfill sites, we have quite strong environmental laws in South Africa, and it's very costly. To dispose to the landfill site would have cost for this project in the equivalent of about $5.7 million. And besides which, we're just purely taking up landfill airspace with sludge. So, disposal of the treatment works. This is where we had a problem. We shut down one of our treatment works. When we took it there, we thought we were doing the right thing. We'd simply wash it in a screening system here. We take all the detritus out, bag the detritus, put it in the sewage works, and that's what a sewage works is for, to treat the sludge. We overloaded the digesters. Nitrogen load was way out. So at the end of the day, we actually closed down that treatment works. It's not a normal treatment works, not designed to take all this additional sludge. And what you normally say is that out of desperation comes innovation. And this is when we started the birth of what we call the DEPA. And the DEPA machine is, we call it the DEPA because it's a nice African sound, and it stands for latrine dehydration and pasteurization. This is the drawings that we drew up in a little office in Cape Town, a couple of mechanical engineers, ourselves, and we come up with a system that looks like that. Basically what it is that you have extruders. So they are screw compacting extruders that have an opening at the far end. So you put your sludge and detritus in one end, it compacts the sludge gets forced through the holes there. Those are 6 millimeter to between 6 and 9 millimeter holes. It squeezes them out like a spaghetti. The detritus passes and can't go through the holes, and that comes out the end of the screw, and that can get bagged. This falls onto an open porous belt that travels around, and it falls in an open matrix, and that's the key to the whole thing, because what you have, as it passes along this open belt, it goes through a pre-drying system, which is the waste heat from the genset, and then it goes into medium wave infrared radiators, and that process from there to there takes about 16 minutes. Yeah, so it's 16 minutes from there to there. It is also a vacuum, so it pulls the hot air through the actual through the porous belt, and when it comes out the other side there, it pours out in a dry pellet form. It's not totally dry; it's around about 66 to 70% solids. When it comes in here, our sludge is coming in at around about 25%, between 25 and 35% solids. When it comes out the other side there, it comes out, it's depathogenized. That's what it looks like. That's what, during the process of building the plant. That is the plant there. This is the screw extruder that runs through the back there. This is the pre-drying set. This is the infrared. That's what the screws, the spaghettis look like when they get rinsed through these little holes and they fall in the open porous belt. That's the end of the machine, and this is what it looks like when it comes out the end. That's what actually happens. Then it gets on site, it gets bagged. Puts it into white bags and ready for transport to where we take it. The whole unit is situated in 2 containers. It's in a 40-foot container and a 20-foot container, and it's all plug and play. You can pick it up, you can take it where you like, and put it down and start operating. Operating costs to purchase a plant, that's in rands, so it's about $640,000 purchase. The average operating cost, we look at back to compare it to a cost. That's 0.5 of a litre of diesel per person per year. If you're looking at treatment works in South Africa, it's around about 0.9 of a litre to 1 litre per person per year. That's your costs. That's changed a little bit now with the $45 petrol diesel price. It has 1 supervisor and 5 general workers. That's all it takes to operate this plant. It's very simple, it's very basic. Tests carried out in the sludge, we are solid capacity. It can cope with solids between 25% and 40%. After that, it's too dry, before it's too wet. Processing, well, we had quite a bad discovery problem in Etequini. Tests were done, and the discovery count on about 50 grams or something like 1,000 eggs. When it went through the process, there wasn't one live egg left. It was carefully looked at by the people in KwaZulu-Natal University. NPK values, it's about 321, but it's very low. It's about 2% per weight. So in other words, your fertilizer is normally sitting about 22% per volume. This is about 2%. We did some trials, some engineering trials. These weren't agricultural trials done by engineers. And what we did was no fertilizer, and we used 3 times the volume of fertilizer in pellets. After 19 days, that's the results. That's on lettuce and spinach. It was actually quite a good fertilizer. This is our new program. How we're going to operate. We as a municipality are going to employ a managing contractor. We will lease this plant in to supply to a managing contractor. So if something goes wrong with the managing contractor, he doesn't walk away with the plant. So we lease the plant in. Managing contractor will then operate the plant for us. He will empty VIPs, and then he will also look at sales of fertilizer to farmers, etc. It can be used as ordinary treatment works, provided it's standard works with digesters and set tanks. We don't do activated sludge because it's too smooth. We put it through the process, we wet it again, it's very, very smooth. So basically what we have there is just a situation where you have an pelletizing plant. It provides a sanitation solution, it provides a health solution, employment for the people that are working in the area, and it's a food security solution. Basically, it's a simple technology, addresses technical and environmental challenges, addresses our political social ambitions via service provision, food sustainability, job opportunities, landfill preservation, gives us subsistence agriculture. It's a low-cost solution, and first of all, it's affordable. Thank you.
Thanks very much. I think it's also a great example of how different sludge is in different places and how different the treatment technologies have to be to cope with that. Like the Durban sludge is very dry and very rubbish filled compared with lots of other places we've seen this week. so just a prescriptive presentation. Are there any questions at this stage?
Hi, I'm Ashok Srivastava from ADB India. Thank you for the excellent presentation. My simple question is this a patented technology with you?
Yes, it is patented, but not through Antiquary. The person that we co-invented it with, they patented it. We have a 10% share of the patent, just to protect our interest in it.
So, is it available in the market now?
It's going to be launched very shortly by an Australian company, I believe, being called Depa Global. So it will be coming to the market shortly. It's on all the websites, so you can get it on the websites.
Thank you so much. Thank you.
I think we had a question here.
Thank you for a very informative and interesting presentation. Vietnam from the National University of Civil Engineering, Hanoi, Vietnam. I like all the process, and I just wonder at the very beginning you mentioned about so the input of your ladder power technology, like is this that from every 5 year recycle, like. Is this a slot that go to your technology? You can, those ones are like collected every 5 years. So I just wonder what a difference, like 5 years collect the slot and 1 or 2 years slot.
Okay, I think I can answer it. We empty our printed cleans once every 5 years. So we have a process. So we sweep the area, we start in one spot and we work our way across Antiquary to get that in. We're just leasing 3 more plants, we have 4 plants. We need 4 plants to treat the amount of sludge that we go through over a 5-year period. So you just purely keep going through the area and that sludge gets treated and pelletized and that pellets will get used. We're using the pellets in our community gardens, community gardeners and in our parks and gardens department we're using it as well at this stage.
Thank you.
I think we'll have to leave the other questions to the end. Sorry. Thank you very much, Dave. Move on to the next speaker. And our final speaker from the day, for the day is from Cameroon. It's Nkezi Nchembeng, sorry. And he will be speaking on a case study in Yaoundé, the potential for struvite precipitation and nutrient recovery from fecal sludge leachate. He has a background in botany and has an MSc in plant biotechnologies, and he's currently doing his PhD whilst working at the Waste River Research Unit.
Thank you very much, moderator, distinguished participants, ladies and gentlemen. Nkezi Nchembeng is my name, from the University of Yaoundé 1. The presentation you're about to follow is a case study that was carried out in Yaoundé that sought the potential of fecal struvite precipitation and nutrient recovery from fecal sludge leachate. Permit me to start by recalling that struvite was discovered in 1845 by the Swedish geologist Ulex, named after his supervisor Gottfried von Struve. It was recognized then as agglomeration of minerals in the form of calculi or stones. But recently in New York, it was reported that these precipitates were blocking pipes of sewers in treatment stations. And this led to some further research with which we came out with an understanding that struvite is actually magnesium ammonium phosphate hexahydrate. It is a sparingly soluble, slow-release bioavailable fertilizer that precipitates naturally according to the reaction on board. Now, extensive thank you. Next slide, please. Extensive studies have been carried out with source-separated urine, and And it was realized that if you have the right adapted reactor, and you add your urine with an external magnesium source, you stir, and you open the taps to release the effluents strategically, you remove the sieve, you dry it, and the precipitate solidifies to form what we have as struvite. What was our interest in carrying out this study? Previous mates of the laboratory conducted some work on fecal sludge leachate and discovered considerable amounts of nutrients in leachate after treating fecal sludge with planted dewatering beds. And since we know that the struvite technology has served as high-end solution to accommodate fertilizer shortages, our intention was to find out if this could also serve as a strategy to polish the leachate we obtained from planted dewatering beds. Hence, the major objective of this study was to precipitate struvite from fecal sludge leachate with an eye on the cost. In order to do this, ladies and gentlemen, we had to obtain magnesium in the form of wood ash from SuSanA in the littoral province of Cameroon. And we had to purchase magnesium chloride, which served as our solid test, mindful of other experiments that have been conducted with it to prove that it's possible. We bought it from Yaoundé. And then we were supplied fecal sludge by mechanized vehicles, emptying trucks. We kept it in a storage container from which it was applied to non-planted dewatering beds. And after some time, we obtained the leachate in vats. To get urine, which served as our control, upon consent with the other officials, the departmental toilets, precisely the male urinal of the Department of Plant Biology in the Faculty of Science, University of Yaoundé, were adapted to and connected to a 5-liter gallon pipe tubing, and with this setup we could collect about 20 liters of urine within 3 to 4 weeks. Prior to precipitation tests, samples of our solvents or solutions were taken to the lab where they were analyzed for physical-chemical parameters, as well as phosphate and nitrogenous nutrients, following standard protocols. Furthermore, an adapted reactor was created from local materials, suiting the model that was used in Nepal by ETA. Our precipitation experiments were conducted in 2 phases. On the one hand, we had to precipitate struvite from urine and from leachate using magnesium chloride as source of magnesium. And on the other hand, we had to do that using wood ash. For each precipitation experiment, we had 3 repetitions, and some other initial considerations had to do with the dosage of wood ash, 15 grams per liter, the dosage of magnesium salt, 4 grams per liter. We settled at 15 minutes for stirring time and 45 minutes for settling time. The drying depended on, of course, the weather conditions. With these, ladies and gentlemen, we came up with the following results. You realize that the pH of leachate is almost neutral as compared to the pH of urine. This was the case both before and after precipitation experiments. We compared here with total dissolved solids, which was also low, 138 milligrams per liter for leachate before, and it dropped after, while we had 444 milligrams per liter in urine, which also increased after. These results are in corroboration with the works of Benda, which explains the fact that when you apply fecal sludge on dewatering beds, there is some consequent mineralization that occurs, and that explains for the pH. Furthermore, studies prove that struvite has a minimum solubility at pH greater than 9 or equal to 9, without which it cannot be precipitated. It was therefore not surprising that in the course of our experiments, we could not precipitate struvite from fecal sludge leachate. However, with urine, we could get some quantities of struvite from the salt, both in the case where we use magnesium chloride and in the case where we use wood ash. This go along with confirm the results of Kolcheve and collaborators, Sativera and collaborators, as well as ETA, struvite precipitates only at a pH greater than or equal to 9. We also compared the nutrient contents, and our results corroborate with the results of Gallman showing that nitrogenous nutrients are highest in wastewater, precisely urine. Furthermore, phosphates are the slightest nutrient content in wastewaters, hence their determinant nature. You must ascertain the fact that you have phosphates in your solution before you can attempt to precipitate struvite. We evaluated the magnesium, the total phosphorus, and the total nitrogen content in our leachate, and we obtained the following results. There was an increase from 0.49 to 3.3 milligrams per liter of magnesium in the effluents after precipitation. And as for total phosphorus and total nitrogen, the gas nitrogen, there was a sharp decrease from 88 to 51 and from 391 to 193 milligrams per liter respectively. These results corroborate with the conclusions of Linda Strandy and collaborators, as well as Kenya in 2000, which all go a long way to declare, first of all, that magnesium is limited in wastewaters, and secondly, that phosphates are the minimum nutrients in wastewaters. We tried to analyze the struvite we produced, and quite interesting was the fact that the magnesium content in struvite from salt precipitation was more than that with ash, while the inverse was true with total nitrogen and total phosphorus, which increased in the struvite produced from wood ash other than the struvite produced using magnesium salt. Our results also revealed traces of sodium, calcium, and potassium in the struvite. Ladies and gentlemen, we conclude by saying that no struvite is produced from fecal sludge leachate, but the results are not enough basis for us to conclude that definitely struvite cannot be precipitated from fecal sludge leachate. It is therefore an ongoing current research proposal that we want to see if we can adjust the pH according to protocols determined or postulated by Lezeng and Ziamini in 2006, which involve titrations with sodium hydroxide and hydrochloric acid solutions to bring up the pH. We are trying to, at this point, manage wood shavings and sawdust. We are thinking of the possibility of incinerating it at a specific temperature as postulated by Sativelli and collaborators to increase the magnesium content, all in a bid to get wood ash as a low-cost magnesium source for the process. So we want to verify at the pH level if that is feasible. And we are also trying to see the possibility of creating a motorized and industrialized adapter with a motorized stirrer. And finally, we want to verify detailedly the composition of the struvite produced, mindful of the fact that we realized that it had some traces of sodium, potassium, and calcium. Permit me to round up by acknowledging the following people, ladies and gentlemen. This research topic was suggested by Ewak Samle, and they directed the work, which of course was carried out at the University of Yaoundé 1. And the work was funded by the Swiss Agency for Development. And last but not least, we are grateful to the Bill and Melinda Gates Foundation who made the presentation possible before you today. Thank you very much.
Thank you very much. Before we go to questions, just an announcement. A wedding ring was lost in this room sometime before 4 p.m. If that was your ring, can you come and find me just now when the questions start? And you can tell me what was written inside it to identify it. If it's not someone in this room, we'll then go and ask around in the other room. So if you come and find me now as soon as the questions start, thank you. Okay, are there any questions at this stage? Elaine.
Hi, is that I could ask for everybody or just this presentation?
Just for the first two questions, and then I'll get everyone up here. Thank you.
Thank you for your presentation. I'd like to know about I see the sulfide is a complex compound.
Yes.
I'd like to know how the availability of the nitrogen, because I think it's the main element you're looking for plants. How is it available for plants in that complex?
Struvite, thank you for your question. Struvite is a slow release bioavailable fertilizer, I earlier said, and it is sparingly soluble. It only precipitates when the pH is above 9. The tests in Ethiopia by Dalecha were presented some time ago, as well as other tests in Nepal by Bastian Eta, have proven that it has a slow, its slow release nature makes it better than many synthetic fertilizers. So I think it is something we are looking at detailedly in the lab. We've not yet come up with conclusions, but for now what we can say is we are thinking that by virtue of its nature as a slow release fertilizer, the elements of erosion and weather don't quickly wash it off the soil, especially in environments like ours where we have rains. So I don't know if I've answered your question. Okay.
Any other questions for Hazel? Jeff?
Thank you. I have just one question. How do you control the proportion while mixing the magnesium source with the urine or with the sticker sludge?
Okay, thank you very much for that question. I'm glad you're asking, and you're somebody in the terrain. I was just talking with you this afternoon with respect to issues of the like. I'm mindful of the fact that it was an innovative work in our environment. We thought it wise to go back to literature. And Sativel and collaborators used about 18 grams of wood ash per liter when working with uranium. So we decided, mindful of the fact that it was a pilot and a test research work, to make it up to 15, since we understand the dynamics of the differences in wood ash content. And then Bastian Eta, working with, I think, magnesium oxide in Nepal, used 4 grams of magnesium source per liter of solution of urine. So we made it up to 5 grams. These are some of the elements we put in place to come up with what I would call supposed measures for the experiment. Does that answer your question? Okay, thank you.
By a miracle, we're running before time, so if I can ask all the speakers to come up now, and we'll have any questions for any of them. So all 6 speakers, if they can come to the front. Question there on the end of the podium.
Hello, thank you for everybody for your presentation. Well, I have only one commentary to addition for the LADEPA process, and one question for the last speaker. About the commentary of LADEPA, I wanted to say if you are interested in see some results about the pellets. Because I forget to introduce myself. I work with David Wilson in Potsdam University, and we have a small LADEPA, a small prototype LADEPA. So if you're interested to see some results about LADEPA, about the drying kinetics and the characterization of the pellets, we have a poster outside, just in the beginning of the hall, at the right, there is a poster of LADEPA if you're interested to see the result. Now, for the last speaker, I have a question. Have you calculated the potential with based on the composition of phosphates of your leachate? Do you know the maximum, the potential production of struvite? Thank you.
Thank you for your question. Our main objective for this study was to verify if at all it's possible to precipitate struvite from fecal sludge leachate. So that would have been a sequel kind of trial. We would have followed up if the results were positive But since the results were negative, we could not do anything to calculate potential. So we hope that at the pH level now, when we adjust the pH, we can ascertain whether or not it's possible to precipitate struvite. Then we'll proceed to calculate potential. Thank you.
Hi, thank you all for your very interesting presentations. I have a question. My name is Hester Foppen from the Netherlands, Aqua for All. I have a question for David Wilson from ETQueen. What would you identify as the major obstacles for the commercial replication of the LaDepa technology? Why wouldn't it be possible to spread it and to scale it at the commercial side?
I can talk for what happens in South Africa. We are looking to do that. We don't have big volumes currently in the Tekwini, but the person who holds the patent on it, he is the person who's going to be licensing the product. So we have to go through our Department of Agricultural and Environment Affairs, and they have to actually then license it with them, and they have to have lots of checks and balances in place to make sure that it's kept at a safe level for distribution. So he will take up that process. We're not going to do it because the volumes that we have doesn't warrant it. We're processing like 10,000 cubic meters a year. Doesn't come close to what we require for fertilizers and moving out of the province. But we will use it internally. But then hopefully if it does start to spread to other areas within South Africa, he will do the licensing and then it will be commercialized.
I can add to that if I may. There will be another presentation tomorrow afternoon which does touch on the factors which affect the viability of treatment processes, including the LaDepa as part of the FSM chain, and sort of the factors that can be adjusted to make it more or less viable. And that is a shameless self-plug for my own presentation tomorrow afternoon. I think the lady up in the green shawl there on the front row.
Thank you. I'm Neeta Pokrit from Asian Development Bank. I think we're all excited about LaDepa. So I hope you keep the name. It's lovely, rolls off the tongue. But we look forward to seeing it in the market. I think the lady touched upon some of my questions. My question was, what are the obstacles you've had, problems that you would say wouldn't work in these situations, but you're saying you're working on that. Also the issue you said it's fairly low cost. What are you talking about for 35,000 picks? I guess it's 35,000 households, correct? So what are we talking about in terms of capital cost there? And up to, has there been any thought on up to what could be the upscaling of it, maximum capacity to what, or maybe you're still working on that, but still excited about that, so thought I'd ask the question. I'll come and visit your poster also. Thank you.
Okay, we are upscaling at the moment. As I said to you, we started with one trial unit. We just right now are busy. We've got a lease route. The cost, as I said earlier, is about $600,000, converting rands to dollars. That's the cost of the plant. We've gone a lease route because it's slightly cheaper, but we also lock the supplier in, whereas he can't just sell us the plant and walk away. So we pay him on a monthly basis over that period of time. So he gets a maintenance contract and a lease contract. So he will maintain the plant for us over that period of time. So that's what we've done. So we're upscaling in the Tekwini. We're going to now be processing all our sludge, all our VIP sludge, because of the possibility of removing the detritus without having to do anything. The machine takes it out on its own.
Gentleman at the back there. Also, just before we have any more questions, if anyone has any comments as to sort of take-home messages from the session, please feel free to share those now as well.
Thanks for your presentations. My name is Sampath Gopalan. I represent Corp for People India. My question is to Mr. A. On the 20th February. I would like to know what is the fill-up rate that in twin pit model, how much time did it take to fill up one pit, and what is the age of the tarling you have tested?
Well, I have understood your first question. Can you repeat the second one?
What is the age of your toilet that you have
Taken for testing. Well, I am answering the first one first. Well, usually it took 12 to 14 months to fill up one pit. And for analysis, we have taken samples that are already 18 months old. Is it okay?
The lady here in the green sweater.
Hi, I'm Elizabeth Ulrich. I work with the Sustainable Sanitation Alliance. I have a question for Alison. And you might already guess what I'm going to ask. That blue liquid, we've talked about it on the SuSanA discussion forum at great length, and people have said, what is that liquid? Why do you need it? Is it environmentally sustainable to have some chemical in that toilet? And the answer was generally, no, that's a secret, we can't really tell you. So my question is now, I have the opportunity to ask you directly, when you have that process that you're going to put in, that blue liquid could give you real headaches, I think. I mean, it is something that's supposed to kill pathogens, so your bacteria in the process will probably also suffer. So I'm curious, what's the theory behind that? You know, are you expecting lower performance because of that blue liquid? And what about advising the clean team to drop that blue liquid? Is it really necessary? So I'm really curious about that.
Thanks, Elizabeth. It's certainly probably the thing that I'm most worried about with this project as we move forward into actually commissioning the technologies and starting the trials is what the impact of that blue liquid is. We've done 2 sets of tests. Different students have done 2 sets of tests on the blue liquid, one of which proved that it didn't really have any biocidal properties and one of which proved that it did. So we'll see what the impact is. I think we're just going to have to see where that happens and if we can manage to make the technology work despite that blue liquid. I think for Clean Team, we've also tried with them a dry toilet where they use sawdust, and the customers didn't like that as much as the blue liquid. I'm really interested to hear from the team working in Haiti who are doing a similar project I just heard about yesterday with, I think it was peanut waste, and they clearly are having more success, but I think the Clean Team customers have got used to the blue liquid and they quite like it, and anything else is a poor alternative. So I think it's a challenge, and if the technologies we don't have work, we'll just have to put our thinking caps back on and find something else. Or the criteria for this phase was to test off-the-shelf technologies. I think by the time we finish this phase, there may well be more off-the-shelf technology, so we may well have more options available to us.
Any other questions or comments on this session?
Hi, I'm Shinji, also from the ABB. My question is to Oswald. So you were actually talking about cow dung versus the quality of human fecal matter, and there was something about some toxicology that you were mentioning. I didn't quite follow that. When you were talking in your slide about the farmers are happy to handle the cow dung, but they're not so they won't touch the fecal waste, and then there was something you were trying to say which I didn't quite understand.
About the slide of this?
There was this slide when you were talking about how the farmers were alright with the cow dung, cow waste, but then you said there's something about human waste which is toxic, or there was some toxicology analysis you were trying to make.
I was trying to compare in Uganda, where we have a lot of cows, cow dung, the smell of cow dung is unbearable. Actually, it's more than the human feces. And people are so happy at handling the smell of cow dung. But I was trying to show the emotions they have when it comes to human waste. I know all of us have pathogens in our bodies. We produce waste with some level of pathogens. But it wouldn't, those pathogens, if it would remain there without being more polluted with other chemicals that we add in the feces, it would be easier for us to manage.
We don't have to be looking at pathogens not like heavy metals. Where do they come from? They come from when we get the way we handle that human feces after coming from the body. Because we mishandle it, because of our perceptions about it. But the cow dung, where people know it's from animals, not from their own bodies, they don't normally waste it. And they are able to use it the way it is, even when it has pathogens, like worms. Thank you.
The question is for my friend from Uganda. I was looking at the results that you know, at the end, your conclusions, and the different didn't meet the standards of, 100 BOE is for Uganda. You have, thought about the reasons behind it, or is it simply the influent BOE so high that it cannot be treated, or is to do something with the design or the sizing of the different units? If you're trying to keep it so compact that maybe if you had a chance to increase the size of your area, maybe you could actually achieve that 100 BOE target.
Thank you for your question. Actually, the plant, we are operating it at high organic corroding rate compared to what we normally get in the Faecal sludge. This project is ongoing, and we are supposed to provide a solution to the best way we can manage Faecal sludge. And every day we are making modifications. So at the moment, if we again test this month and we haven't made any improvement, we can maybe edit the loading rate. For example, initially we used to load it with about 800 liters. It was so bad, then we reduced, and now it's improving. So at the end, we may get an accurate loading rate of our system so that we can meet the discharge standards. If not, then we employ other techniques, maybe the tertiary treatment techniques instead of a constructed wetland.
Yes, actually I'm going to ask three of you. The first question is going to be for Alison. So for the SuSanA BioBosa is kind of aerobic gravel filter. So like, is this do you encounter the smell? Because this is like the sludge, and usually there's a lot of smell, and then you use the aerobic kind of technology. So do you have any problem with this odor at all?
So we haven't finished commissioning the technology yet, so I don't know. I mean, SuSanA BioBosa have tried the system in Mexico, and I wasn't aware that they had any complaints on that. It will, for the ultimate application, it will depend where it is. At the moment, it's sat next to some solid waste stabilisation ponds, so the smell is not going to be a problem. Where Clean Team move to in the future, if they're going to be kind of more integrated, they're really out of the city at the moment. If their future treatment work is going to be done quite close to their customers, then the smell is certainly going to be something we're going to need to consider.
Yeah, just keep in mind because it's mostly they use anaerobic technology like that, so just keep in mind.
Yeah,
thank you. So my second question is for Osbert. Yes, again, for the sludge treatment, mostly I know that they use a lot the anaerobic digester. Then for your DFAS process, you use ABR and then followed by anaerobic filter and followed by anaerobic planted gravel filter. So have you ever compared? If you add a lot of treatment units, and of course it's going to be better quality, but then have you ever compared if with the research that or that they just only use screening, sedimentation, and then anaerobic digester? Have you ever compared?
Yes, we've done that comparison, and we find the highest removal efficiency is recorded in the ABR system. And even actually we expect that's what the literature says, and we normally get about 50% reductions compared to other units in the ABRs. So in case we are going to improve, maybe we concentrate more of improving the FBR system, maybe having more units than the other systems, since we are getting the highest efficiency there.
It seems so, yeah. So if there's in your presentation, we'll have kind of economic analysis, like compare how much dollars per cubic meter treatment that you use the fast compare with the traditional or more conventional one. I think so.
Okay.
Thank you. And yes, the last question for Dave Wilson. Sorry if I ask many questions. In Vietnam, I think they already treat the fecal sludge, and they had problem with selling fertilizer. There's no market for, like, very little market. So, for example, for your experience, because you did some research and pilot in, I think, in Africa, is it? So, do you have any problem with selling the fertilizer? Any advice? Because you know why? Like now, I'm sorry, like chemical fertilizer made in China is much cheaper than organic fertilizer. So we cannot convince Vietnamese farmers to use organic. So far, we lost, we failed. So, do you have any advice?
Yeah, it's a case of trial. Once they've tried it and they see the results they get, it's something that we've given to the agriculturists, and they haven't been able to tell us why it works so well. Some guys say it's the organics that are in the material, some guys say something else, some guys say it's bound, that the N, P, and K is bounded in slow release, you don't get washout like you get with fertilizers. But what I have found, and we are currently running trials with the University of KwaZulu-Natal, agricultural trials, where they're trying struvite and pellets and so on and so forth, and those results will be made known sometime shortly. But just on our own little homegrown trials, I'm going to say that it's quite noticeable that the yield increases on the plant. So if you're planting eggplant, and under normal circumstances you can have up to 5 eggplant on a plant, you're getting up to 8 or 9 where you've got pellets. For some reason, I don't know why. I'm a civil guy, I'm not an agriculturist, but that's what happens. And we've given it to some of the market gardeners, not people that are using it for their own goods, for their own vegetables. So we give it to the market gardeners who sell on, and they're crying for it. They keep phoning saying, when can we get more, when can we get more? We say, not yet, it's not licensed yet. But, so it's just a case of, when they try it and find out how well it works, I think it's going to explode, yeah.
Give it for free for like a couple of crops, right?
100%, yeah. What they used, we gave away.
Thank you. Anybody else? Yep, on the front row.
Morris Gold from SuSanA. I have a question to Osbert. Thanks for your presentation. I find I find decentralized fecal session very interesting, also in the urban setting. Even if it's just, I don't know, dewatering or some separation and an ABR and then discharging maybe the liquid into the sewer. I don't know how it can look like. What's in terms of legal regulations in the peri-urban or urban setting in Uganda? Who do you need to talk to in terms of discharging then the effluent into a water body or into a drain, or how does it look like?
For this pilot project, we contacted the City Authority. As I've said, they are part of our partners in this research. But if you're going to scale it up, the best person to talk is the National Environmental Management Authority in Uganda.
Yeah.
Maybe time for one last question if anyone has one. Otherwise, I think we need to wrap it up. Okay, great. Thank you very much to all our speakers. For me, I love this topic from a chemical engineering point of view because the feedstock is so difficult and so variable and so unpredictable. It just makes it very interesting, but also very challenging. I think we touched on it a bit, but the issue of decentralization of these treatment plants and the impact that has on the whole business model for the entire chain is very important. So so in terms of both transporting the sludge to the plant and then transporting the product away. Sort of one of the things that might be part of Alison's field, as she looks at me in terror, is the time that the sludge spends in the pits or in the toilets, and again the impact that that has on the treatment process and the economics of the whole thing. So there's an awful lot of factors that fit in together, and definitely something that we need to keep working on. So thank you again to all our speakers for their brilliant presentations, and thanks to the